Welcome everyone. Today we are going to learn about one important feature of action potential. That is, action potential propagates down the action toward the action termini. But the most interesting fact is it does not spread backward. The question is why it does not spread backward. To understand, at first I want to explain how neurons work. As you can see, these are the dendrites that receive electrical signals from other neurons. Now the integration or summation of all these electrical signals occur in the axon hillock, where action potential initiates. And the axon actually conducts the electrical signal or action potential. And in the axon termini, the transmission of these electrical signals occur by secretion of neurotransmitters. So in a way, we can say that all the parts of the neurons actually works differently. Now the question is why action potential does not spread backward, and the answer is it is due to the inactivation of voltage gated sodium channel. Now in my previous video I have already mentioned that voltage gated sodium and voltage gated potassium channels is responsible for the generation of action potential, but in this video I will only focus on voltage gated sodium channel. If we zoom these portions of the actions, we will find that here many voltage gated sodium channels is present. Now what happens when the integration or summation occurs? The membrane potential actually increases. In general, in resting conditions or unexcited neurons, the membrane potential remains approximately minus 70 millivolt. But when the membrane potential of the neuron rises and it meets or exceeds the threshold potential, that is approximate minus 50 millivolt, certain number of voltage gated sodium channels opens in the initial segment. And through that voltage gated sodium channels, sodium actually enters inside the neuron because the outside concentration of sodium is high and inside is low. And we know that ions move from higher to lower concentrations. So when this voltage gated sodium channels opens during this voltage difference or voltage change, the sodium flows inside the axons, and that's called active current. So when sodium flows through the sodium channel, we will call it active current. But the excess amount of sodium that enters inside the axons can diffuse short distance and can depolarize the adjacent segment, and that causes the opening of more sodium channels, and sodium enters through the sodium channels, and it also actually spreads passively. So this is called passive current. So for the generation of action potential, both the active and passive current of sodium is important. The sodium channel has a dynamics that it opens very quickly in fractions of milliseconds, less than 0.1 millisecond, but it inactivated within 1 millisecond, from 0 to 0.5 to 1 millisecond. Now it remains inactive unless the membrane potential becomes less than minus 70 millivolt, that is the hyperpolarization. That means this conditions requires the help of voltage gated potassium channels. So unless it remains inactive, and then it closes when it hyperpolarizes and remains closed for 4 milliseconds, that is the refractory period. So once a sodium channel, voltage gated sodium channel opens, it quickly inactivates and remain closed. So the passive spread of the current from by these sodium ions can activate or actually open the adjacent segment voltage gated sodium channels. Now the sodium that enters through this sodium channels can actually passive spread, but it cannot reopen the inactivated voltage gated sodium channels. It can activate the adjacent segments away from the actions and the sodium channels. So initially these sodium channels remain closed, but when passive current flows, it depolarises, it opens, and sodium enter inside